Hello, how are you? Hope things are going well. More magnetism. So last time we talked about magnetism in terms of wires, loops, solenoids, and we used Ampere's law and Biot-Savart law, neither of which I'd really recommend memorizing, especially since you get both of them on your formula sheet. But there are a few formulas you should memorize. One of them was magnetic field. We use B for that. Due to a line. I like to do a cursive L for the line. Does not matter. Mu naught I over 2 pi r. And then we had magnetic field due to a, let's call it a loop at Z, which was mu naught I r squared over 2, then it was Z squared plus r squared, and then it was to the 3/2. This one's kind of a pain to memorize. Just grab a piece of paper, write it down a bunch of times, and ingrain it into your soul. You really only need to know this for this class. So after you take the AP test, you can just throw it out. Well, throw most of it out. Keep a little residual memorizing of it. So, and then we have B to magnetic field of a loop where Z equals 0. So you have like a loop like this, the magnetic field at this point right there. So then that would just be where Z equals 0. So you can use your above equation and plug in 0 for r squared, or for Z, and you get r squared to the 3/2. Whoop, whoop. The 2's cancel. Some of the r's cancel, and you're left with mu naught I over 2r. And the mnemonic I help to differentiate between the line and the loop is when you have a line, you have a circular magnetic field around the line. And the circle makes me think of 2 pi r. And for the loop, you have no pi involved because in the center where you're looking, the magnetic field is straight up and down. Again, that's 100% mnemonic because this mu naught is 4 pi times 10 to the negative 7th. So when you expand out that mu naught, that pi disappears. So it's not, my mnemonic is not grounded in reality. It's grounded in helping you remember the formula. Straight memorization. And, ooh, I forgot the solenoid. Clean up this right there. Okay. Magnetic field due to a solenoid. So this assumes that the magnetic field within the solenoid is uniform, which is a reasonable approximation depending on how good an approximation you need, which is mu naught I times number of loops divided by length of the solenoid. So you have a solenoid. Is this a solenoid? Do something like this. So these are a bunch of loops. So this will be length. The number of loops here will be N. The current will be I. And then to find the direction, you wrap your fingers around the solenoid in the direction of the current. So let's say it's going this direction. So you wrap that way, and then your finger points towards the direction of the magnetic field. And this is similar to finding the direction of the magnetic field due to a line, which is of a loop. So for a line, place your finger along the direction of current, and then your fingers are the magnetic field. That was a crooked magnetic field. And then for a loop, wrap your fingers along the direction of current, and your thumb will then show the direction of magnetic field. Okay, so that was a quick review of the things you should have in your head. So let's go on to some problems. So this is a free response problem. I never like free response problems as much. Like, there are a lot of really cool multiple choice problems which you're just kind of like, oh, well, that's clever. But then you move on quickly and it's done. kind of like a small piece of chocolate. It's a quick, instant pleasure, instant gratification, and you move on. Free response, it's a lot of work. Luckily, this one doesn't have any graphs. Oh, I hate graphs. So tedious. So tedious. Okay, focus. So we have a circular loop of wire, figure 1. Check. Above has a radius of r. Okay. It carries a current I. I believe it. Point P has a radius of r over 2. Aha. Above the center of the loop, express algebraic answers. 2 parts alpha and Bravo, A and B, okay? In terms of R, I, and fundamental constants. State the direction of magnetic field at point B1. That's right there. Field B1 at point P due to the current in the loop. Okay, so this is the right-hand rule. Fingers in the direction of the current, wrap it around the loop, points upwards. So then we have magnetic field going up. So A dot I dot upward. Whoop. Okay. Calculate the magnitude of the magnetic field at field B1 at point B. Okay. Man, my reading is not as good as I'd like to think it is. I should work on that. Okay. So this is a loop where you're not, where Z is not 0. But they do give you Z, it's R over 2. And we derived this, I think, as the Biot-Savart law. I would not recommend deriving it for this point because you only got like 15 minutes to do this problem, which is not a lot. So trying to make sure you get all the cosines and sines right. It's not saying you can't do it, but it's a minefield. You can make so many mistakes. And you're better off just remembering what the formula is. Okay, so we write up the formula. Ooh, cyan. That's a good contrast with blue. You say Z equals R over 2. R over 2? Yep, because that's where point P is. So then we'll have a Z squared, which equals R squared over 4, because 2 squared is 4. And then if we do R squared plus Z squared, we're going to have 4R squared over 4, because that's just R squared, plus R squared over 4 gives us 5R squared over 4. Okay, so that's good. Now, equals. So I'll do mu naught I R squared over 2. And then I'm going to do 5/4 to the 3/2 times R squared to the 3/2. So what I did was I distributed this 3/2. So that part right there is 5R squared over 4. And I distributed the 3/2 exponent to each of the parts of the, to the 5/4 and the R squared. So if you don't believe me, which is good, I like that questioning attitude, you could look at something like, I don't know what, 3 times 2 to the squared, and that should equal 3 squared times 2 squared. So this is 6. 3 times 2 is 6, 36. And that should equal 3 times 3 squared, which is 9, times 4, which also equals 36. Now that's not a proof, that's just a one shot in the dark, making sure we're not completely incorrect. Whoop. So yes, I believe I can do that. Blue? Blue. Dark blue. Okay. So now we need to work our way through this. So this part will go away. So R squared and 3/2. 3/2, man. So I'm just going to write this all out. So we got, and then so we're going to have 3 r's up there. These will cancel. So we'll have mu naught I all over 2. And then I'm going to write 5 cubed as 125. Because 5 times 5 is 25. Times 5 is 125. Then we'll square root that. Divided by 4 cubed, which is 4 times 4 is 16. 64. 64 square rooted is 8. I'm going to check that one real quick. So 4 to the 3 halves equals 8. It does. It does. That's totally true. Because like 4 to the 3 halves equals 4 to the 1 half cubed. 4 to the 1 half is square root of 4, which is 2 cubed, which is 8. So yes. Go math. Algebraic. Is that algebra? I'm not actually sure. Okay. And then this will become 4. And then we're left with 1 r over here. So this is mu naught I over r times 4 over square root of 125. Okay? I think I can simplify this though, because this is 25 times 5, and we take the square root of both. And so this becomes mu naught I over r times 4, 5 times the square root of 5. And I know it's gauche to sort of have a square root in the denominator. Some people call it radicals in the basement. No hippies in the basement. But, yeah, it's fine. I'm good with this. So our answer to this first part, here I'm going to circle this. I love how I said circle, and I specifically square it. Group it. Woohoo! Nice. And then I'm going to erase pretty much most of this because I like a clean board. Except I erased what I wanted to keep. Okay. Go away. Go away. And move up here. And then that part can go away. Calculate the magnitude of the magnetic field at point P. And that's up here. Yes, true. And it's hopefully it's kind of easy to see where you only have 15 minutes to do this problem, but it is really easy to get bogged down. When you start looking at some of those, taking numbers to the 3/2 power, like cubing them and then square rooting it, that can take a lot of time. Luckily, you won't be distracted by crystal light. Delicious, delicious, purple flavored crystal light. A second identical loop, also carrying a current I, is at a distance r above the first loop. Okay, so if it's r above the first loop and point P is r over 2 above the first loop, then the second loop is r over 2 above the point P. So what we're told then here is this distance right here is also then r over 2. 1/2 plus 1/2 equals 1. Determine the magnitude of the net magnetic field at point P. Okay, so we're given the current direction. Kind of hard to see there, but it's going this way. So right-hand rule, magnetic field for this goes up. Magnetic field for the first one goes up. So, and since Z can be either positive or negative, it's not going to matter. The net magnetic field for this will just be mu naught I over r times 2, which I'm just going to write 4 times 2 is 8, over 5 square root of 5. So we just double it. Super easy. It's kind of funny how like that first problem easy, second problem crazy hard. Not crazy hard, but if you don't know the formula, it's like, But if you know the even if you do know the formula, there's a lot of little math you need to worry about. And then B, also super easy. And so these questions, they're also not, in terms of points, they're not all weighted equally. So I imagine that the second part would be weighted far more than the first or B. A small loop of wire in which each side has length S, okay, right there, is now placed at the point P, okay, with its plane parallel to the plane of each loop, okay, as shown in the figure 3 above. Also okay. For parts C and D, assume the magnetic field between the two circular loops is uniform. That's a big assumption, but okay, we'll go with that. In the region of the square loop and has magnitude B net. In terms of B net and S, determine the magnetic flux of the square loop. I'm not sure if we talked about flux yet, but, well, we might not talk about magnetic flux, but we've talked about electric flux and flux in general. So the idea with flux, I'm going to write it as phi, then I'm going to do a B, say magnetic, will equal magnetic field times area. So magnetic flux would then just be B net times S squared, which is mu naught I over R times 8, 5 square root of 5. That's a terrible square root. Square root of 5 times S squared. Yep. Oh. Wait a sec. So this is actually the answer they're looking for right here. Us doing that extra step and making their life easier, totally unnecessary. Maybe even wrong. Okay. The square loop is now rotated about an axis in its plane at angular speed omega. In terms of B net, S and W, calculate the induced EMF in the loop as a function of time. T, assuming that the loop is horizontal at t equals 0. I have told you nothing about EMF yet, but I'm going to give you a 2-second tutorial and we'll just do the problem. So EMF equals d flux dt. D flux dt. And huzzah, bam, got it. So depending on where you started the time there, I might have actually made it under the time limit. Okay, so the square loop is now rotated about an axis, okay, in its plane at angular speed omega. In terms of B net, S and W, calculate the induced EMF in the loop as a function of time, assuming that the loop is at horizontal t equals 0. Okay, so we know that flux equals B times A. So this part you need to remember to do the product rule for derivatives. So this would be dB dt times area plus B times dA dt. So we assume that we have a constant magnetic field, and so dB dt equals 0, but the area for the flux is going to be changing. And that is going to be changing like cosine omega t. Is that true? So at time t equals 0, it's you have maximum flux. So cosine of 0 would be 1. So it would have maximum flux. Yes. Oh, times S squared. We need an S squared in there. And as time goes on, it'll turn vertical, which will be 0. Yep. Which will then come back to S squared. Yep. But we also need to do derivative with respect to time. So this is area with respect to time. So as time goes on, that cosine is going to take into account the rotation. Ooh, I forgot one thing. I was wrong about this. It's supposed to be negative d flux dt. There we go. Wonder why things felt funny. There we go. Okay, so now to find out the induced EMF, which is basically just a voltage. It's a generator action. We need to do the derivative of cosine omega t, which is sine omega t. Derivative of cosine is sine. No, I think it's negative sine, because the derivative of sine is positive cosine, derivative of cosine is negative. Then we need to do the chain rule, basically take the derivative of the inside, and two negatives, and then we have an s squared. So we are left with a total induced electromagnetic force equals b omega s squared times sine omega t. And that will be the induced EMF. We'll talk more about induced EMF later. That's just kind of a, hey, here's an equation, here's how you do it. You see induced EMF, you write E epsilon equals negative d flux dt. You write flux as magnetic field times area. Do the product rule, and then just plug in everything you have. And the trick here was realizing that when you have a spinning square like that, it's going to be the area of the square maximum times cosine omega t. Generally, whenever you have things spinning, you're either going to have a sine or a cosine relation. Okay? I think this would be a good time to go on to the next one. Okay, so here's a multiple choice problem. My preferred. I enjoy multiple choice, even though it does tend to be an all or nothing type endeavor. They're more exciting. Two long straight parallel wires are held fixed as shown above. Okay? The voltage is applied to wire X. I see how there's an arrow on the X but no arrow on the Y. That's because the only a voltage on X. Creating current IX to the right. The wire experiences a magnetic force of magnitude FB toward wire Y. Creating a current to the right. The wire experiences a magnetic force toward Y. Assuming the resistance of wire X is constant, which of the following graphs correctly illustrates the magnitude of the magnetic force F on wire X as a function of voltage V applied to the wire? Okay, so I'm suspecting there's a current going through wire Y. We're just not told about it. And so there's some mystery magnitude current on Y, because otherwise there wouldn't be a force between the two. So, well, mostly. Assuming the resistance of wire X is constant, okay? What that's saying is that for, so what that's getting at is it says current equals V over R, or alternatively, V equals IR, that if resistance is constant, then current is proportional to voltage. Which of the following graphs correctly illustrates the magnitude of the force F on wire X as a function of voltage V? Okay, so there are equations we'll talk about later about how to look at the force on a wire. As a mnemonic, it's a terrible mnemonic, but the mnemonic that's used by the Navy is fire incinerates little bunnies. F equals IL cross B. I know, I do not personally incinerate little bunnies, nor do I appreciate fire incinerating little bunnies. But fire incinerates little bunnies is the mnemonic for the force on a wire due to a magnetic field. But for this case, it's easier not to use this and just think of it more in fundamental case. So, assuming the resistance of the wire X is constant, which is the magnitude correctly illustrates the magnitude of the force F on wire X as a voltage of V applied to the wire. So, there is some mystery voltage on Y, and it's creating a magnetic field like such. And we're assuming that this is constant. So if we look at each individual piece of current that's moving, current implies positive charges moving in the positive direction, even though in reality it's negative charges moving in the negative direction. So if we look at the force on the individual charges, the electrons, or we'll call them positrons this time, they're not positrons, but positive charges moving in the positive direction, plus QV cross B, what we have is voltage applied, a magnetic force toward wire I. So we have a force down this direction. So we're assuming no electric field, and we're given this equation here for the force on a specific individual piece of charge within the wire. So what it's saying here is as voltage goes up, current will go up linearly, proportionally, and current is just the change in charge with respect to time. So you can think of this as a very similar equation here, because V cross B, since they're parallel, this will be, you can think of the velocity here as a distance divided by seconds, and then Q is just a charge. Well, if you, in terms of dimensional analysis, if you move this S over here, you're going to get Q charge per second, which is basically current. And then you're left with meters and magnetic field. So these two are very similar equations. Man, I've been speaking for probably like 3 or 4 minutes now, and I've gotten nowhere towards answering the question. And you only have like a minute to answer this? Outrageous. Okay. So as voltage goes up, the current goes up proportionally, and that current is going to be directly related to the force. So the more current you have in the wire, the more magnetic force it's going to feel, because the amount of charges moving is going to be directly proportional to the voltage. So long story short, we want a graph that is linear. So it's going to be this one. If you look at the beginning here, they're going to all be 0. If there is no current flowing through X, then there's going to be no attraction between the wires. So that basically cancels out this one and that one because they don't start at 0. We know that as current goes up, it can go up forever. It's not going to level out at some point. So this would be like a capacitor or something. So it can't be that one. And so we're left with, well, is it an exponential or is it linear? And this is what they're talking about here, is you have to realize that V equals IR, there's going to be a linear relationship between current and voltage, and then there's a direct relationship between, or I guess a linear relationship between current and force. And so everything is going to be a linear relationship, which means that you're not going to have this sort of exponential up. And so the answer here would be D. As you increase voltage, you'll increase current, which will increase the force between the two wires in a proportional manner. Okay, let's go on to, I think this is a multi-part problem. Get some of the more parts. Okay, part 2, or 7, or whichever one this one is. 2 long straight wires fixed to magnetic. Okay, and that's just the summary. Which of the following could be true of wire Y? It carries current in the same direction as current X. Okay, so here, I'm going to erase everything over here. I'll even erase this guy. So it's asking us which direction the current's going. So the current's probably even going to go in left or right, with X or against X. And for this, I'm just going to use the equation we always use for a charge. So force equals electric field times Q. That vector should be on the E. That's okay, I'm going to cancel it out anyway. And we know that the force is going this direction. So what we need to do, and so the charges are moving, so Q is going this direction because its current is positive charges moving in the positive direction. Positive charges are positive. And so what we don't know is B, but we know the force. So if we just assume, so we can pick two directions. We'll pick that it's going with X first. So Q, V, cross, okay. So, let's say we have current going this direction. Then the magnetic field is going to go like that. So, like that. And so at this point, we're going to assume that the magnetic field is coming out of the board. So V cross B out of the board would create a force going down. So that seems correct. If you did the opposite direction, where the current on Y was going this way, then you find the magnetic field by wrapping your hand, and you'd have a magnetic field that goes like this up at this point. And so then you'd do V cross B, and you'd have a force going up. So when you have parallel wires and they're attracted to each other, the currents will be going in the same direction. And that all comes from force equals QV cross B. So the way you attack this problem is to backtrack a little bit. You're given charge, you're giving velocity, because you're talking about wire X. You need to find the magnetic field. So you guess a direction. It'll be either left or right for the other wire. You draw the magnetic field, which will be a circle around the wire. You then look at how the magnetic field is going to be at a specific point where the magnetic field intersects the wire, which in this case will be out of the board because you do your right-hand rule. And then you test your force, V, which is the charges moving in wire X, cross B, out of the board, and then the force to be the direction of your thumb, which should be down, which is what they said, so therefore we know that 1 will be correct. Okay, so two long straight parallel wires are held fixed as above, a voltage applied to wire X creating a current, and the wire experiences a magnetic force FB towards wire I. Which of the following can be true about wire Y? Experience a force directed away from X. Okay, so this one just doesn't make sense. So this is saying that you have a wire like this. This is wire X being pulled downward, and then you're going to have a wire Y also being pulled downward. That's not possible because if you're pulling something, you're going to be pulled towards it. Think one of Newton's laws, equal and opposite reaction. So from a physics first semester point of view, you know that Y has to be pulled upwards. So the wires have to be either pulled together or pushed away from each other. They can't have both be pulled in the same direction. Unless there's like some sort of third mystery force. So, nope. It experiences a force of different magnitude. No, this is just, this is saying that the force on Y is different than the force on X. No, equal and opposite reaction. So, when we look at force equals EQ plus QV cross B, and this time we're talking about on X, the velocity of the currents, that has to do with the current through X, IX. And the B, the magnetic field, happens to do with the current from Y. Because the stronger the current is through wire Y, the stronger the magnetic field is going to be around it, and the stronger the magnetic field is going to be where wire X is. So if you look at force Y then, the force on Y is going to be EQ 0 plus QV cross B 0. So these B's and the V might be different, but this V has to do with the current going through Y, because that's the change in charge per unit time. And this B will be the magnetic field due to X. So this will be due to current going through X. And if you look at these, I know V cross B is not the same as B cross V. You can't switch around the cross product like that. But since they're both parallel, the angle will be the same. And so what you're basically doing is you're multiplying them in opposite sides when you do this. I know that sounded really confusing. Idea is they both influence each other, and so you have to have the same force between them. Here you're multiplying QV cross B, and here it's almost like you're multiplying QB times V, but one has to do with I, one has to do with X, one has to do with Y. So they're going to be directly related to each other, and you can't have one that's bigger than the other. You could also go back to Newton's laws, where they say equal and opposite reaction in terms of forces. So 3 cannot be true. And you're left with B as the only possible answer. Or, I guess, 1. Oh, let's do one more multiple choice. Clickety-clack. Clean up the board. Okay, so we have 2 long straight parallel wires, same ones again. And we have a force from X to Y. If the distance between the 2 wires is tripled, what is the magnitude of the new magnetic force exerted on X? Okay. So we can look at F equals E times Q plus QV cross B, which is the same as F equals I L cross B, because this goes to 0, and basically you're just moving one of the dimensions over from the velocity to the charge. But I like to use this one more because it intuitively makes me feel better. And we know the magnetic field due to Y is, so what we want to do is we want to find out how B changes. So the magnetic field due to a line equals mu naught I over 2 pi r. Therefore, if r increases by 3, the magnetic field will decrease by 1/3. And so F equals QV cross B, and this is all going to be on X. And if the magnetic field drops by 1/3, then the force on X will drop by 1/3. Because this is basically the current flowing through X, and the current flowing through X will stay the same. But the magnetic field will drop by 1/3 because X is now further away. The distance has tripled. And so the magnitude of the force exerted on X from B will drop to 1/3 of its original. And so these don't really make sense, because it doesn't make sense why, with wires got further away, why they would have more impact on each other. That would be, nope, doesn't make sense. You might be like, well, maybe it'd stay the same. And then I could see why people would see that it'd be squared, but it's not. So this all has to do with the magnetic field given by a line. Okay? And those are some questions, basic questions you might see with magnetic fields, wires and lines, and circles and loops. We'll start talking about magnetic induction and some of the implications of such next time. Appreciate it. Thank you much.